Welcome to Theory of Computation. This is lecture number 12. In the last lecture, we discussed decidability. We looked at a lot of questions about Turing machines, context-free grammars, linear-bounded automata, and proved that some of them were decidable and the others were not decidable. The most difficult questions we looked at came from Turing machines. Almost all the questions we asked were undecidable. For example, given a Turing machine and an input for that machine, it's undecidable to tell whether the machine will accept that input or not. We cannot design an algorithm to do that task. That was the halting problem. And that was the fundamental undecidable problem. We use this problem to show that many other problems are undecidable. For example, we showed that given a Turing machine, it's undecidable to tell if the Turing machine accepts the empty language. We also looked at questions concerning context-free grammars. And for example, we showed that the emptiness problem for context-free grammars was solvable in the sense that we can write an algorithm which will take as an input a context-free grammar and eventually tell us whether the grammar generates a string or not. On the other hand, if we want to tell if the language generated by a context-free grammar is the set of all strings, that is an undecidable question. Then we looked at linear-bounded automata. We realized that the halting problem for linear-bounded automata is decidable. Given a linear-bounded automata and a string w, we can design an algorithm which will analyze the linear-bounded automata and the string and tell us if the linear-bounded automata will accept that string or not. The main reason we could do that is because a linear-bounded automata uses only linear amount of space. We use that fact to argue that if that machine takes too many steps, then we can be sure that it's in an endless loop. And therefore, we can stop our simulation and say that this machine is not going to accept this input at all. In the end of the last lecture, we looked at another problem. That problem was called the post-correspondence problem. Post-correspondence problem is a very different problem. It's not like the other questions which concern language theory, which are about Turing machines or about other models of computation like linear-bounded automata or push-down automata or DFAs. The post-correspondence problem is simply a puzzle. This puzzle is a very interesting puzzle. What you're given is a set of dominoes, and each domino has something written on top of it and something written on the bottom of it. What you're allowed to do is take these dominoes and make lists by placing one domino after another, and you're allowed to repeat dominoes. So one way you can think about it is that you're given unlimited supply of each domino. Your goal is to arrange these dominoes in a list which we call a match. We get a match when we read the string on the top of the dominoes and the string on the bottom of the dominoes, and both these strings match. In that case, we say the post-correspondence problem has a match. What we want to show now is that this innocent-looking problem, which seems to be just a puzzle, is also undecidable. The outline of today's lecture is going to contain mostly the proof of the fact that the post-correspondence problem is undecidable. Let's look at the outline. Today we will discuss the post-correspondence problem. After that, we will prove that the post-correspondence problem, which we will call the PCP, is undecidable. This would be the bulk of this lecture. After that, we would discuss what are computable functions, and in the end, we would look at the notion of reducibility. So let us begin. We have to start by studying the post-correspondence problem. So let us define the post-correspondence problem very carefully. The post-correspondence problem is a puzzle. You're given dominoes, a set of dominoes. Each domino has a string written on top of it and a string written on bottom of it. And what you are allowed to do is make lists using these dominoes by placing one after the other. And here the important thing is you're allowed to repeat a domino. What your goal is to try to come up with a match, is to try to come up with a list in which when you read the top string or all the strings that are at the top, you get one long string, and you read the bottom string, they are exactly the same string. In that case, we will say that the post correspondence problem has a match. Otherwise, we would say that it does not have a match. So let's look at a few concrete examples to make ourselves familiar with this problem. The PCP problem is a puzzle. We are given a collection of dominoes, each containing two strings on each side, meaning the top and the bottom. A domino looks like this. This particular domino that you see on your screen has A written on top of it, and on the bottom it has AB written. So that's how one domino looks like. The PCP is a collection of dominoes. So you will be given a collection of dominoes. Let's look at a collection of dominoes. Here is a collection of dominoes. This collection consists of 4 dominoes. The first domino has a B on top and a CA on the bottom. The second domino has an A on the top and AB on the bottom. The third domino has a CA on the top and an A on the bottom. The fourth domino has ABC on the top and C on the bottom. So that's how the input for the PCP problem looks like. It is just a collection of dominoes. Of course, this collection will be properly encoded in some form or the other. So you will get a string which is an encoding of a collection of dominoes. We are very familiar with encoding, so we will not elaborate on that point. So you can think of the input to the PCP problem as a collection of dominoes. Let's go ahead. We can make a list of dominoes by placing them next to each other. We are allowed to repeat dominoes. For the collection that we have seen already, we can make the following list. The first list is as given to you on the screen. We place the domino B over AC. Then we place the domino which has CA on top and A on the bottom. Then we place the domino which has A on the top and AB on the bottom. We place the domino which has CA on the top and A on the bottom. So that is one list we can make. In this list, if I read the string that is formed by the top of all the dominoes, I get BCAACA. Whereas if I read what is given to me by the bottom of the dominoes, I get CAABA. Since these two strings don't match, this list is not a match. If these two strings have to be equal for me to say that this list corresponds to a match. For this particular collection, this list is not a match, but the next list that we'll see is a match. The second list consists of the domino A, which has A on top and AB on the bottom. The second domino has B on the top and CA on the bottom. The third domino has CA on top and A on the bottom. The fourth domino has A on top and AB on the bottom. The fifth and the last domino has ABC on the top and C on the bottom. Let us read what do we get if we read the top of all the dominoes. We get ABC, AAA, BC. Let's now read what do we get if we read the bottom of each domino. We get ABC, AAA, BC. In both cases, we get the same string. So this is a match for this collection of dominoes. The PCP problem is, I will give you a collection of dominoes and ask you if you can find a match. The key point here is that you are allowed to repeat dominoes. To find a match, you can repeat dominoes as often as you want. Let's look at the problem formally. Let's start by looking at this other collection. This collection has 3 dominoes. ABC on top and AB on bottom, that's the first domino. CA on top and A on the bottom, that's the second domino. ACC on top and BA on the bottom, that's the third domino. For this collection, I claim that you can never find a match. Why is that? Well, let's have another look at this collection and look at it a bit carefully. You will notice that in this collection, each domino has a longer string on the top than on the bottom. So if I start making a list, using this collection, no matter what I do, the top string will always be longer than the bottom string. So this particular collection does not have a match. On the other hand, the previous collection we saw had a match. So, given a collection of dominoes, some of them have a match and the other ones don't. Telling which ones have a match and which ones don't is exactly the post-correspondence problem. The post-correspondence problem formally is the following. Given a collection P of dominoes, does P have a match? We can turn this problem into a language, as we usually do, by defining PCP to be the set of all encodings of collections of dominoes which have a match. So, PCP is the set of all encodings of P such that P is a collection of dominoes which has a match. Note that the post-correspondence problem is very different from the other ones that we have studied. It apparently seems to have nothing to do with Turing machines or any other model of computation. It just seems to be a puzzle. So, we have studied undecidability of questions which concern models of computation. In fact, Turing's original argument was a sort of a self-referential kind of an argument, because Turing machines can take Turing machines as input. He was able to use that to diagonalize and prove that the halting problem is undecidable. On the other hand, the post-correspondence problem looks very innocent. It's a simple statement, it's a simple question which seems like a puzzle. What you can do is first think about how would you design an algorithm which solves the post-correspondence problem. Well, for that you will have to think about a way of taking a collection of dominoes and analyzing it and seeing if you can find a match. One way to do is to keep trying and look for a match. What you can do is you can make all lists of size 1 and see if you get a match. Then make all possible lists of size 2 and see if you get a match. Then all possible lists of size 3 and see if you get a match, and so on and so forth. However, since you are allowed to repeat dominoes, therefore the length of your list could be arbitrarily large. So if you don't find a match, you'll continue going and going and going, and there doesn't seem to be a clever way of knowing when to stop this search. However, this argument does not show that the PCP is undecidable. As we have seen, simply because we fail to design an algorithm for a problem, that does not mean that the problem is not decidable. It may just mean that we are not clever enough. To show that a problem is not decidable, we must actually construct a formal proof that the problem is not decidable. Once we have proved that the problem is not decidable, we can be sure that no algorithm can ever decide that problem. So how will we go about proving that the PCP is undecidable? The theorem that we want to prove is that the PCP is undecidable. The technique that we are going to use is the one that we have used before. What we will do is we will assume that the PCP is decidable, and therefore there's a decider for it. We will use the decider for PCP to construct a decider for ATM, the halting problem. And that would be a contradiction, since we know that the halting problem is undecidable. So, if we are given a Turing machine M and input to it W, we would look at this Turing machine M and the input W, and by looking at it and analyzing it, we will come up with a collection of dominoes P. This collection will have a match if and only if M accepts W. So, in some sense, what we will do is encode the problem of the acceptance problem for Turing machines into this collection. This collection will have a match if and only if the machine accepts W. And once we do that, we will be able to show that the post-correspondence problem is undecidable. Let's look at how we will go about it. Before dealing with the post-correspondence problem, let's start working with a slightly modified version of the post-correspondence problem, the PCP. We would call this modified version the MPCP. M stands here for the modified PCP problem. The modified PCP problem is exactly the same as the post correspondence problem, except for in this case you are required to start your list with the first domino in the collection. In the original PCP, there's no restriction. You could start your list with any domino that you wanted. But in the modified PCP, there's a restriction which says that you must start your list with the first domino that is given in the collection. So this is the modified PCP. We will first show that the modified PCP is undecidable. Once again, the main idea is that given a Turing machine M and input W, we will describe a collection P prime of dominoes such that M accepts W if and only if P prime has a match starting with the first domino. The main idea would be that this collection will somehow simulate the computation of the machine M on W. So if somebody were to write down a list which is eventually going to be a match, they will have to be simulating what the Turing machine M will do on input X. The proof is slightly complicated and it's in 7 parts, and we'll go through it slowly. Let's begin. Suppose you have a Turing machine M. So this Turing machine is described to you by Q, sigma, gamma, delta, Q naught, Q accept, and Q reject. So all the ingredients of this Turing machine are given to you. And suppose you're also given a string W, which is equal to W1, W2, all the way up to Wn. What we will do is we will make a domino which has a hash sign at the top and hash sign followed by Q naught, W1, W2, all the way up to Wn, followed by another hash sign at the bottom. Well, let's look at this domino. So part 1 is to put this domino which has a hash sign on the top and hash sign followed by Q naught, W1, W2, all the way up to Wn, followed by hash sign in the bottom in your collection. What does the bottom part of this domino remind you of? You're right, that is the initial configuration of this Turing machine M on the input W. So the first domino contains the initial configuration of M on W, and the top domino contains only a hash sign. Now we will add more dominoes to this collection so that we will be forced, since we are starting with this domino, remember that the modified PCP requires you to start with this first domino. The other dominoes will be placed in the collection so that in order for you to find a match, you will have to start simulating the computation of M on the string W. Let's have a look at it. Since the first domino, hence the bottom string, is the initial configuration of M on W, to get a match, one must choose dominoes that are consistent with the bottom. We will add those dominoes in the collection in such a way so that the second configuration of M will appear at the bottom if we are going to match the first configuration, and so on and so forth. Let's look at what are the dominoes we are going to add. Part 2 of this construction is to add dominoes in the collection by looking at the transition function of this Turing machine M. So we will examine the transition function of M, and then we'll add appropriate dominoes to our collection. This is the most important part of this proof because this actually encodes the workings of the Turing machine into the collection. Let's have a look at it. Suppose that we have delta of Q comma A equals R comma B comma capital R, where Q is not equal to Q reject. In this case, what we will do is put the domino which has QA at the top and BR at the bottom in our collection. So if the Turing machine in state Q, after reading A, goes into the state little r, writes a B and moves to the right, then we will have a domino which has QA at the top and RB at the bottom. The basic idea is when we encounter the string QA at the bottom, and we want to match it, we will be forced to choose this domino, and this would force us to write down RA on the bottom string and therefore help us go into the next configuration of the Turing machine. What would we do if the machine moves left? That's part 3 of the construction. Part 3 of the construction says the following. Suppose that we have A, B, C, which are in the work alphabet, and Q and R are 2 states, where Q is not the reject state. In this case, if delta of QA is equal to R, B, L, then we will put CQA and RCB in our collection. So this will also help us simulate one step of the Turing machine and move into the next configuration. Let's look at part 4. In this case, for every tape symbol A in gamma, for every symbol in the work alphabet, we will put a domino which has A on top and A at the bottom in our collection P prime. The purpose of these dominoes is to simulate the computation of M on W. Since this construction is so elaborate, it would help us if we looked at an example. So let's look at an example. Let us say that gamma is 0, 1, 2 and the blank symbol. So our work alphabet has just 3 symbols, 0, 1 and 2, and the usual blank in it. And let's say the input is 0, 1, 0, 0. And let's say the start state of M is Q0. Then the initial configuration of this machine is Q0, 0, 1, 0, 0. So in this case, we will add one domino, one starting domino, which will be hash sign at the top and hash sign Q0, 0, 1, 0, 0, hash sign at the bottom. Now suppose that delta of Q0, 0 is equal to Q7, 2, R. The part 1 places the first domino, which is hash sign at the top and the initial configuration surrounded by hash signs at the bottom. So we have the initial configuration at the bottom. This is how the match begins. In order for the match to continue, we want to pick a domino that has Q0, 0 on top. Now, remember that we place dominoes which had states in them in part 2. In fact, in part 2, we place the domino Q0, 0 at the top and 2Q7 at the bottom. That's because delta of Q0, 0 goes to state Q7, writes a 2 and moves to the right. That's what the machine did, and we placed this domino. So we must use this domino to continue the match. Let's look at what happens. Now the match would look like we will have Q0, 0 at the top and the initial configuration at the bottom, followed by 2Q2. Now we want to continue the match. Remember that we also placed all dominoes which had A at the top and A at the bottom. We can use those to continue our match. If we use several of these dominoes, we will eventually reach the following partial match that we have constructed. This match, what is shown to you on the screen, at the top you will have hash sign followed by Q0, 0, 1, 0, 0, which is the initial configuration of the machine, whereas on the bottom you have hash sign followed by Q0, 0, 1, 0, 0 hash sign, then it is followed by 2 Q0, 1, 0, 0. This is quite amazing. This is really amazing because what we have is at the top, the initial configuration is copied, but at the bottom, after the initial configuration, we have the machine after it has taken a single step. So what we have done is simulated one step of the Turing machine. Notice that all the dominoes that we placed were in some sense forced. We had no choices. And therefore, what happened is, in order to get the first match at the top, the first string which was initially given to us at the bottom, in order to get it at the top, we were forced to put the next configuration at the bottom. We would like to continue this. Let's look at this example further. Now in part 5, what we will do, the following two dominoes in our collection. The first domino is hash sign at the top and hash sign at the bottom, and the second domino is hash sign at the top and a blank followed by hash sign at the bottom. Why are we putting these two dominoes in our collection? Well, the first one is obvious. What we want to do is also be able to copy the hash sign so we can continue on to the next configuration. The hash sign is a separator between configurations, and we want it to be there so that we can continue to the next configuration. The second domino is slightly more interesting. It is replacing a hash sign with a blank hash sign. So it allows us to insert blanks to the right of the configuration. Remember that when we write our configurations, we do not write the blanks that appear to the right of the last symbol. So if we have a configuration, say Q0101, that actually represents that we have an infinite tape. The machine is in Q0 and the tape has 101 followed by infinitely many blanks. When the tape head wants to move to the right and it wants to read a blank, we must take care of it. This domino allows us to do that. So this is part 5 of the construction. Let's continue further and see what happens. Now delta of Q7, 1 is Q5, 0R. So when the machine is in state Q7 and it's reading a 1, it will go into state Q5, write a 0 and move to the right. So in this case, we will place the following domino in our collection. It will have Q7, 1 at the top and 0 Q5 at the bottom. So what we will do is, in this case, if we follow the same method as before and try to get a match which continues, we will finally reach the following partial match. In this match, at the top we'll have the initial configuration separated by a hash from the second configuration, which is 2Q7100 hash. On the bottom we'll have the initial configuration, the configuration that the machine was after making one step, and then followed by the configuration that the machine would be in if it were to take 2 steps. So this is quite amazing. At the top, if we have, let's say, 10 configurations listed, at the bottom we will have the 11th one forced on us. Now when we try to match the 11th one at the top, that will force us to write the 12th configuration, and so on and so forth. So this way, what we are doing is forcing a match to happen only when we are following what the machine is doing on the input W. Let's continue. So far we have only looked at examples when the machine moves to the right. Now let's take example when the machine moves to the left. Let us say delta of Q5, 0 is equal to Q9, 2 and L. This means when the machine is in state Q5 and it's reading a 0, it goes into the state Q9, writes a 2 and now moves to the left. In this case, remember, we did not just add one domino for this transition, but we added several ones. Let's look at them. We added 0 Q50, Q902, 1 Q50, Q912, and so on. The last domino was a blank Q50, Q9 blank 2. So these are the relevant dominoes that we placed for a transition move which moves to the left. Let's continue. Now the match at the bottom, we must use the domino 0 Q50. If we use this domino and then copy dominoes, then at the top we will have 20 Q500 written, and at the bottom we'll have 2 Q9020, that configuration written. So you see we have a configuration, second configuration, third configuration, and let's say fourth configuration written on the bottom, and we have 3 configurations written on the top. In order to continue this partial match, we want to copy whatever the 4th configuration is at the top, and when we do that, we are forced to put the 5th configuration at the bottom. So each time we copy the configuration from the bottom to the top, we are forced to write the next configuration at the bottom. So what we're doing is, each time we do this, we are going into the next configuration and the next configuration and the next configuration, and all these choices are forced. We don't have any other choice. So this way, what is happening is, this partial match is actually simulating what the machine M will do when it's given the input W. Let's continue. In order to construct a match, we must simulate M on input W. However, there's a problem. The top string is always behind the bottom string. The top string, if it has 12 configurations, the bottom string has 13. If the top string has K configuration, the bottom string will have K plus 1 configurations. That means the bottom string is always going to be longer than the top string. So how are we ever going to get a match? Actually, this fact is really good for us, because what we would do is we would allow the top string to catch up with the bottom string only when we reach an accepting configuration. That's the next part of the construction. Let's have a look at it. We will only allow the top string to catch up with the bottom string once we go into an accept state. So this is part 6 of this construction. For every A in the tape symbol, we will put A Q accept at the top and Q accept at the bottom as a domino, and Q accept A at the top and Q accept at the bottom in our collection. The first domino allows the accept state to eat up symbols from the left side. The second one allows the accept state to eat up symbols from the right side. Now let us say we construct a partial match and eventually we reach an accept state. What we can do is use these 2 dominoes repeatedly to start eating up whatever is written on the tape. We are not doing this to simulate the behavior of the machine anymore, but just to allow ourselves to complete this match since we have reached an accept state. Let's look at an example. Suppose that we have the following situation. We have reached the configuration 21 Q accept 002. Now we can use the domino QA0 QA to get to the situation where we are in the configuration at the bottom, which is 21 QA2 hash symbol, which means we ate up a 0. We can use the other dominoes in part 6 to finally reach a match where we have a hash sign which maps the first hash sign at the bottom, and then we have a QA followed by a hash sign. So what we have to do is we have now nearly completed our match. If we just do the last part, we will be able to finish this and complete this partial match into a complete match. That's what we are after. So let's look at part 7 of this construction. We finally add the following domino. This domino has QA and 2 hash signs at the top and just a hash sign in the bottom. And we add this to our collection, and this last domino will allow us to complete our partial match. Once we have gone into accept state, use the dominoes to eat up all the symbols that come around the accept state, we will be in the following situation. So the summary of this construction is given as follows. The first domino has the initial configuration on the bottom and only a hash sign on the top. To copy any configuration on the top, we are forced to put the next configuration on the bottom. By doing this, we simulate M on W. When we reach the final state, we allow the top to catch up with the bottom string. That way, if M accepts W, we will find a match. On the other hand, if M does not accept W, we will never be able to find a match in this collection of dominoes. Let's see why would we not find a match in this collection of dominoes if M does not accept W. If M rejects W, then there is no match, because remember that the bottom is always ahead of the top, and we start eating up the bottom only, or allow the top to catch up with the bottom only when we reach accept state. If M ever rejects its input, we will not reach the accept state, and so if we follow the construction that is given, we'll never be able to get a match. What will happen if M loops forever on its input? In this case, the top will once again never catch up with the bottom string, and therefore there will be no match in this collection. This is an elaborate construction which takes a Turing machine M and an input W, and from there constructs a collection of dominoes, a collection such that if you start with the first domino, you will get a match if and only if the Turing machine M accepts W. If the Turing machine M does not accept W, this collection will not have a match. So, we have proved the following theorem. Let us state this theorem very clearly. If P prime is constructed as described, then it has a match if and only if M accepts its input W. Now, we have finished this construction. Now we can use this construction to prove that the modified PCP is undecidable. The proof is going to be as our previous proofs. We will assume that the modified PCP is decidable. We would take a decider for it. Since it's decidable, therefore there is a decider for it, and we will use this decider to construct a decider for ATM, the acceptance problem for Turing machines, or the halting problem, which would be a contradiction. So let's look at the proof. Let us assume that the modified PCP is decidable. Let us say we have a decider R for modified PCP. Let us consider the following decider S. On input M, W, where M is a Turing machine and W is a string, we construct a collection P prime as described in the 7 parts that I have just told you. Now we run R on P prime. If R accepts, then we accept M, W. If R rejects, then we reject M, W. Since P prime has a match if and only if M accepts W, therefore S accepts exactly ATM. It accepts all pairs M, W where M accepts W. However, this is the halting problem, and so S becomes a decider for the halting problem, which is a contradiction. This contradiction tells us that the modified PCP is not decidable. So we've been able to show that the modified PCP is a puzzle which is undecidable. Well, we did not want to show that the modified PCP is undecidable. We wanted to show that the post-correspondence problem is undecidable. But we are almost done. As most of the work is already done, now what we will do is just finish our job and show that the original post-correspondence problem is also undecidable. Let's have a look at that. Our next theorem is that PCP is undecidable. Note that what we constructed was a collection P prime. P prime was not an instance of the post-correspondence problem, but an instance of the modified post-correspondence problem. So, what can we do in order to show that the post-correspondence problem is undecidable? Well, what we can do is we can tinker this collection P prime that we have shown as follows. Let us say that we have a string U, which is U1, U2, U3 all the way up to UN, and let us define the following 3 strings. The first one is star U, the second one is U star, the third one is star U star. Star U is equal to star U1, followed by a star U2, followed by a star U3, and so on. U star is going to be U1 followed by an asterisk, followed by U2 followed by an asterisk, so on, up to UN followed by an asterisk. Whereas star U star is going to be an asterisk followed by U1 followed by asterisk followed by U2 all the way up to UN followed by an asterisk. So star U, what it does is it inserts an asterisk before each character of U. U star inserts an asterisk after each character of U. And star U star inserts an asterisk before and after each character of U. So these are three strings. Let's continue. Suppose we have an instance of the modified PCP problem P prime. So we have P prime, a collection of dominoes, and let's say this collection is given by the first domino has T1 at the top and B1 at the bottom. The second domino has T2 at the top and B2 at the bottom, and so on. And the collection consists of K dominoes with TK at the top and BK at the bottom in the last domino. So here each TI and BI is a string. Suppose we have this kind of a collection for the modified PCP problem. Notice that the modified PCP problem has a restriction. You must start with your match with the first domino. Well, we can now study this new collection for the original PCP problem which has no restrictions. Let's look at that collection. That collection, the first domino is star T1 at the top and it has star B1 star at the bottom. The second domino has star T2 at the top and B2 star at the bottom. The third domino has star T3 at the top and B3 star at the bottom. And the last domino has star TK at the top and BK star at the bottom. Then we add an additional domino which has a star diamond at the top and a diamond star at the bottom. Well, if you closely look at this collection, what do you observe? Let's look at this collection once again and look at all the top and the bottom strings that appear in this collection. You will notice that all the top strings start with a star. On the other hand, if you look at the bottom strings, the only bottom string that starts with a star is the one that corresponds to the first domino of the original modified PCP problem, namely the domino which has star T1 at the top and star B1 star at the bottom. Now, if anyone were to find a match for this new collection, they will have to start with the first domino. Therefore, we do not explicitly need to say that find a match in this collection which starts with the first domino. That restriction is somehow implicit in the collection. Therefore, now we can consider this collection as an instance of the PCP problem. Notice that the stars aren't really doing much here, only forcing that the match should start with the first domino. In this collection, any match will start with the first domino since it is the only one that has the first character on top and the bottom which is the same. So we don't have to insist that a match has to start with the first domino. It is implicitly built in the collection. Other than forcing the first domino to start the match, the stars don't put any restrictions. They simply interleave with the other symbols. The last domino that we added, which had a star and a diamond and a star, can be used in the end to finish off the last star that needs to be matched. This means instead of asking for a match for the modified PCP problem which has a restriction that you must start with the first domino, we can now give this collection and put no restrictions. The restriction is implicit. So this becomes an instance of the PCP problem. This shows us that the PCP problem is also undecidable. Let's look at the formal proof. The theorem says that the PCP problem is undecidable. Let us assume that the PCP problem is decidable. let's say we have a decider R for PCP. Well, now let's consider the following decider S. It gets an input P prime, which is an input for the modified PCP problem. By looking at this P prime and the asterisk trick that we have done, it now constructs a new collection P for the PCP problem. Now it runs R on P. If R accepts, it accepts P prime, and if R rejects, S rejects P prime. Then S is a decider for modified PCP, which is a contradiction because we've already shown that the modified PCP is an undecidable problem. So this shows us that the PCP puzzle is undecidable. There cannot be an algorithm which takes a collection of dominoes and tells you whether there is a match. This is an amazing thing we have proved. Well, when you actually look at the proof, you realize that the PCP problem does seem to have something to do with Turing machines. That's because we were able to simulate the behavior of Turing machines on this PCP question. We were able to repose the problem whether M accepts W into a collection of dominoes and asking whether this collection of dominoes has a match or not. But if you were to show this problem in its initial form to someone, it would take them a lot of time to realize that this problem has anything to do with Turing machines. This is a very simple problem, a very simple puzzle. In fact, PCP is, to many people, a very natural problem which turns out to be undecidable. This was Post's contribution to computer science. He gave us an extremely natural problem which does not seem to have anything to do with Turing machines, which is undecidable. Let's go further today and let's discuss the next topic that we are going to continue in the next lecture. We want to talk about computable functions. So far, we have looked at Turing machines, and these Turing machines have two special designated states, accept state and a reject state. And what we do is we give an input to a Turing machine, and this Turing machine either accepts the input or rejects the input. So in other words, this machine either says yes or no, and therefore it accepts a language. Now we want to be not just able to say yes or no, but actually compute a function. So for example, suppose you give two numbers to a Turing machine. You want the Turing machine to do some computation and then produce an output which is, say, the sum of these two numbers. Let us define or discuss these Turing machines briefly, and then we will discuss what computable functions are. So now we will consider Turing machines that compute functions. These Turing machines will have an input tape and an output tape. A diagram of this Turing machine will look like this. Now, let us consider a function which maps sigma star to sigma star. So this function takes strings and maps them to strings. So for example, it may take binary representations of numbers and compute the binary representation of the square of a number. So, but this function goes from sigma star to sigma star. We say that this function is computable if we can find a Turing machine which, when we give it the input W, will write down f of W on its output tape and halt. So a function is computable if we can find an algorithm to compute this function f. Note that some books or some authors do not require the Turing machine to have a separate input and output tape. However, we will discuss these details in the next lecture. I'll see you next time. Thank you and goodbye.